Proof, divisibility, congruence, reals. Vocabulary. Divides, multiple, divisor. A is congruent to B modulo n. Absolute value, the triangle inequality. Symbols. For integers a and b with a not equal to 0, we say that a divides b if there is some integer c such that b equals ac, and we write this. If a does not divide b, then we write this. If a divides b, then 1. b is a multiple of a, and 2. a is a divisor of b. Note that 1. An integer n is even if and only if 2 divides n, and every even integer is a multiple of 2. And 2. An integer n is odd if and only if 2 doesn't divide n. To prove, let a, b, and c be integers with a not equal to 0 and b not equal to 0. If a divides b and b divides c, then a divides c. Strategy. Consider a direct proof where we show that c is a multiple of a. Proof. Since a divides b and b divides c, then b equals ax and c equals by, where x, y are integers. So, we have the following. Since d is an integer, then a divides c. To prove, let x be element of integer. If 2 divides x squared minus 1, then 4 divides x squared minus 1. Strategy. Consider a direct proof as some manipulation, and then recalling a proven result. Proof. Since 2 divides x squared minus 1, then x squared minus 1 equals 2y, where y element of integer, and we have this. From this, note that x squared is odd, and therefore x is also odd, since we had proven that x squared is odd if and only if x is odd. Since x is odd, we can write x equals 2z plus 1 for some integer z. Now, we have the following. Since a is an integer, then 4 divides x squared minus 1. To prove, let a be c element of integer, where a doesn't equal to 0. If a does not divide bc, then a does not divide b, and a does not divide c. Strategy. Rather than a direct proof for the implication, consider the contrapositive. Implication. If a doesn't divide bc, then a doesn't divide b, and a doesn't divide c. If p, then q. Contrapositive. If a divides b or a divides c, then a divides bc. If not q, then not p. Without loss of generality, we'll prove the a divides c case only. Proof. Assume that a divides b or a divides c. Without loss of generality, assume that a divides c. Since a divides c, then c equals ak, where k element of integer. So, we have the following. Since d is an integer, then a divides bc. We can apply proof by cases if we know the remainders of integers. When an integer n is divided by 2, the remainder will be 0 or 1. From this, every integer can be expressed as n equals 2q for even n, or n equals 2q plus 1 for odd n. When an integer n is divided by 3, the remainder will be 0, 1, or 2. So n is n equals 3q, or n equals 3q plus 1, or n equals 3q plus 2. The parity of n restricts possible values of r. For example, although every integer could be expressed as n equals 4q plus r, where r equals 0, 1, 2, or 3, if we only wanted the odds, then we'd have n equals 4q plus 1, or n equals 4q plus 3. To prove that x element of integer, if 3 divides x, then 3 divides x squared, while if 3 does not divide x, then 3 divides x squared minus 1. Strategy. Direct proof for the first part, proof by cases for the second part, since if 3 does not divide x, then either x equals 3q plus 1, case 1, or x equals 3q plus 2, case 2, for q element of integer. Proof. Since 3 divides x, then x equals 3q, where q element of integer. So, we have the following. Since I is an integer, then 3 divides x squared. For 3 not dividing x, we have two cases. Case 1. When x equals 3q plus 1 for some integer q, then we have the following. Since I is an integer, then 3 divides x squared minus 1. Case 2. When x equals 3q plus 2 for some integer q, then we have the following. Since I is an integer, then 3 divides x squared minus 1. To prove, let xy element of integer. Then 3 divides xy if and only if 3 divides x or 3 divides y. Strategy. Because of the biconditional, 3 divides xy if and only if 3 divides x or 3 divides y, p if and only if q. There are the implication and the converse to prove. Implication. If 3 divides xy, then 3 divides x or 3 divides y. If p, then q. Converse. If 3 divides x or 3 divides y, then 3 divides xy. If q, then p. Rather than a direct proof for the implication, consider the contrapositive. Implication. If 3 divides xy, then 3 divides x or 3 divides y. If p, then q. Contrapositive. If 3 does not divide x and 3 does not divide y, then 3 does not divide xy. If not q, then not p. For the converse, that is, if 3 divides x or 3 divides y, then 3 divides xy, we have two cases. 3 divides x, 3 divides y. This will be proven with the previous case using without loss of generality. Proof. Assume that 3 divides x or 3 divides y. Without loss of generality, assume that 3 divides x. Since 3 divides x, then x equals 3z, where z element of integer. So, we have the following. Since a is an integer, then 3 divides xy. Now assume that 3 does not divide x and 3 does not divide y. Then either x equals 3p plus 1 or x equals 3p plus 2 for some integer p, and y equals 3q plus 1 or y equals 3q plus 2 for some integer q. Explicitly, there are four cases. X equals 3p plus 1 and y equals 3q plus 1. We'll do this one and we'll omit the other one since they're similar. X equals 3p plus 1 and y equals 3q plus 2. X equals 3p plus 2 and y equals 3q plus 1. X equals 3p plus 2 and y equals 3q plus 2. Case 1. X equals 3p plus 1 and y equals 3q plus 1, where pq element of integer. Then, we have the following. It follows that there is a remainder of 1 when xy is divided by 3, and so 3 does not divide xy. Cases 2, 3, and 4 result in similar situations. For integers a, b, and n greater than or equal to 2, we say that a is congruent to b modulo n, symbolically, this, when n divides a minus b, which is a minus b equals nx. Regarding integers x and k, note that even integers x satisfy x congruent to 0 mod 2, since 2 divides x minus 0, which is x minus 0 equals 2k. Odd integers x satisfy x congruent to 1 mod 2 since 2 divides x minus 1, which is x minus 1 equals 2k. To prove, let a, b, k, and n be integers where n greater than or equal to 2. If a congruent to b mod n, then ka congruent to kb mod n. Strategy. For a direct proof, we assume that a minus b is a multiple of n, and then we need to show that ka minus kb is a multiple of n. Proof. Assume that a congruent to b mod n. Then n divides a minus b. Hence, a minus b equals nx for some integer x. Therefore, we have the following. Since kx is an integer, then n divides ka minus kb. Hence, ka congruent to kb mod n. To prove, let a, b, c, d, n element of integer where n greater than or equal to 2. If a congruent to b mod n and c congruent to d mod n, then a plus c congruent to b plus d mod n. Strategy. For a direct proof, we assume that both a minus b and c minus d are multiples of n. Then we need to show that a plus c minus b plus d is a multiple of n. Proof. Assume that a congruent to b mod n. Then n divides a minus b. Hence, a minus b equals nx for some integer x. Similarly, since c congruent to d mod n, then c minus d equals ny for some integer y. Adding these two equations, we get the following. Since x plus y is an integer, n divides a plus c minus b plus d. Hence, a plus c congruent to b plus d mod n. Proof. Let a, b, c, d, n element of integer where n greater than or equal to 2. If a congruent to b mod n and c congruent to d mod n, then ac congruent to bd mod n. Strategy. For a direct proof, we assume that both a minus b and c minus d are multiples of n, and we do a bit of manipulation. Then we need to show that ac minus bd is a multiple of n. Proof. Assume that a congruent to b mod n. Then n divides a minus b. Hence, a minus b equals nx for x element of integer. Similarly, since c congruent to d mod n, then c minus d equals ny for y element of integer. From this, we get the following. Multiplying these two equations and subtracting bd, we get the following. Since nxy plus dx plus by is an integer, n divides ac minus bd. Hence, ac congruent to bd mod n. The proof. For every integer n, either n squared congruent to 0 mod 3 or n squared congruent to 1 mod 3. Strategy. Consider the two cases from a previously proven result. Let x element of integer. If 3 divides x, then 3 divides x squared, while if 3 does not divide x, then 3 divides x squared minus 1. Proof. There are two cases, 3 divides n or 3 does not divide n. When 3 divides n, then 3 divides n squared, and so n squared equals 3x for x element of integer, n squared congruent to 0 mod 3. When 3 does not divide n, then 3 divides n squared minus 1, and so n squared minus 1 equals 3x for x element of integer, n squared congruent to 1 mod 3. To prove, if n is an integer, then n squared congruent to n mod 3, unless n congruent to 2 mod 3. Strategy. Consider the three different remainders when n is divided by 3. N congruent to 0 mod 3, n congruent to 1 mod 3, n congruent to 2 mod 3. For each case, consider the previously proven result, that x element of integer, if 3 divides x, then 3 divides x squared, while if 3 does not divide x, then 3 divides x squared minus 1. The goal of this proof is to show that n squared divided by 3 will have the same remainder as n divided by 3, unless n has a remainder of 2 when divided by 3. Proof. We have 3 cases. If n congruent to 0 mod 3, then 3 divides n, and so 3 divides n squared. So n squared congruent to 0 mod 3, thus n squared congruent to n mod 3. If n congruent to 1 mod 3, then 3 does not divide n, and so 3 divides n squared minus 1. So n squared congruent to 1 mod 3, thus n squared congruent to n mod 3. If n congruent to 2 mod 3, then 3 does not divide n, and so 3 divides n squared minus 1. So n squared congruent to 1 mod 3, thus n squared not congruent to n mod 3. To prove, let xy element of real number. If xy equals 0, then x equals 0 or y equals 0. Strategy. Consider a direct proof by cases where we assume xy equals 0 and wish to show that x equals 0 or y equals 0. Consider the two cases, x equals 0, which is already our desired result. X does not equal 0, where we have to show that y equals 0. Note that here, 1 over x exists. Proof. Assume that xy equals 0. We consider two cases, according to whether x equals 0 or x does not equal 0. Case 1. If x equals 0, then we already have the desired result. Case 2. If x does not equal 0, then 1 over x exists, and we can multiply our initial equation by it. Xy equals 0. 1 over x xy equals 1 over x times 0. 1 over x xy equals 0. Now we look at the left side to show that y equals 0. Note that 1 over x xy equals 1 over x times y, 1 times y, y. And so y equals 0. The absolute value is defined as absolute value equals x if x greater than or equal to 0, negative x if x less than 0. Often proofs involving absolute value x are proofs by cases. To prove the triangle inequality, for every two real numbers x and y, absolute value x and y less than or equal to absolute value x and absolute value y. Strategy. If either x or y equals 0, then the inequality becomes an equality. If both x and y are non-zero, then we will have 4 cases. X greater than 0 and y greater than 0, x less than 0 and y less than 0, x greater than 0 and y less than 0, x plus y greater than or equal to 0, x plus y less than 0, x less than 0 and y greater than 0. Proved with the previous case using without loss of generality. Proof. If either x or y equals 0, then we have equality. Absolute value x plus y equals absolute value x plus absolute value y. Now we assume that x and y are non-zero. Case 1. If x greater than 0 and y greater than 0, then x plus y greater than 0. Now we have the following. Case 2. If x less than 0 and y less than 0, then x plus y less than 0. Now we have the following. Case 3. One of x and y is positive and the other is negative. Assume without loss of generality that x greater than 0 and y less than 0. Now we consider these two subcases. Subcase 3.1. If x plus y greater than or equal to 0, then we have the following. Subcase 3.2. If x plus y less than 0, then we have the following. In conclusion, combining all the cases, we have, for every two real numbers, absolute value x plus y less than or equal to absolute value x plus absolute value y.